When a heavy industrial pump begins to shake or a pipeline ruptures, the immediate investigation often focuses on a loss of pressure. This focuses on the moment the pressure suddenly drops or disappears. Pressure loss is a secondary symptom. The core of the failure lies in the mismanagement of the fluid's total energy. Miscalculated energy levels manifest as immediate physical destruction. These forces tear through internal seals, leading to pipe ruptures and the violent mechanical breakdown of pumps, known as cavitation. Safety professionals use fluid physics to locate these specific failure points before the system is ever pressurized, shifting the focus from reaction to prediction. Constructing a predictive model requires analyzing the microscopic state of the fluid, the geometric constraints of the pipe network, and the overarching laws of energy conservation. Replacing reactive assumptions with rigorous fluid physics provides the only reliable method for preventing industrial catastrophes. To understand systemic failure, we begin by observing fluid behavior at a microscopic level inside a single pipe. This behavior is quantified by the Reynolds Number, or RE. This dimensionless ratio dictates flow behavior by comparing the inertial forces driving the fluid forward against the viscous forces resisting that motion. A Reynolds number below 2000 indicates the laminar flow regime. The fluid moves in highly stable layers, following parallel paths that minimize internal resistance. Between a Reynolds number of 2000 and 4000, the fluid enters the transitional flow regime. Here, the parallel stability begins to degrade as the opposing forces interact. Above 4000, the flow becomes turbulent. Multi-directional vector loops form within the pipe, resulting in chaotic energy loss. Laminar flow is rare in high-volume environments. Most industrial systems operate entirely within this turbulent regime. Because industrial flow is inherently turbulent, engineers must assume a baseline of internal chaos and energy loss before factoring in the physical geometry of the pipes. Those physical constraints are governed by the continuity equation, Q equals A times V, where Q is flow rate, A is area, and V is velocity. As the cross-sectional area of a pipe decreases, the fluid velocity must increase to move the same volume through the restriction. This forced high velocity causes internal erosion and severe vibration, which eventually compromises the mechanical integrity of the system. The diameter equation reveals exactly how these area changes impact system pressure. The variable for diameter, d, is raised to the fourth power. This relationship means that even small reductions in diameter yield exponential increases in pressure loss. Having the diameter of a pipe forces the fluid to move 4 times faster. Seemingly minor design choices in pipe geometry create exponential risks across the entire network. Operators often attempt to resolve low flow rates by dialing up pump pressure, assuming the output will increase proportionally. The flow and pressure equation disproves this linear assumption. The ratio of flow rates is equal to the square root of the ratio of pressures. As seen here, doubling the pressure does not double the flow. Because flow depends on the square root of pressure, the actual output gain is significantly smaller than the energy input. Attempting to force a system with excess pressure stresses the infrastructure, while failing to move a proportional volume of fluid. This square root constraint is also applied at the system endpoints, using the nozzle equation. Pressure equals flow divided by a discharge constant squared. Operators cannot override these physics with raw horsepower. Treating fluid dynamics as a linear relationship leads to mechanical failure. We must also examine energy trends across a macro-level view, such as a long run of pipe leading to a fire suppression sprinkler. Friction loss acts as a constant drain on total system energy over long distances. Friction is determined by 4 variables: the fluid's flow rate, the pipe diameter, internal material roughness, and the total run length. In reality, fire suppression systems fail when friction consumes the available pressure before the water reaches the sprinkler head. Bernoulli's principle explains how this energy is conserved and transformed within the enclosed pipe. Bernoulli identifies an inverse relationship. As velocity increases due to a restriction, the internal pressure must decrease. This low pressure shift can trigger cavitation. Vapor bubbles form in the fluid and instantly implode against the interior wall, allowing the fluid to tear into the pipe material. System starvation and cavitation represent the mathematically certain endpoints of unmanaged friction and extreme velocity shifts. Viewing the pipe network through these principles reveals the invisible forces that determine the life or failure of the system. Success in failure prediction depends on 3 pillars: monitoring diameter for the power of 4 effect, managing friction to ensure endpoint delivery, and controlling velocity to prevent pressure shifts. Executing these calculations in the field requires these foundational constants, starting with the baseline weight of water at 62.4 pounds per cubic foot. These values provide the conversion between physical head and pressure. 1 foot equals 0.433 psi, and 1 psi equals 2.31 feet. Using these variables allows safety engineers to identify the exact point where a system will fail before construction ever begins. Engineering a safe environment requires the uncompromising application of these fluid dynamics to every node of the system.